Good afternoon, everybody. My name is Ben Mawdsley. I'm a data scientist at the Hartree Centre, which is another part of STFC, but based at Daresbury Labs near Warrington. That kind of works to, promote the adoption of machine learning, big data technologies. And it was one of the many cogs in this CReDo project. A couple of my colleagues here are also really important on this project, and they'll be talking in this talk as well. So in the first section, I'm going to introduce CReDo broadly, and then Jethro is going to go through a demonstration of what was actually built, and then Jens is going to talk about how DAFNI really helped that become possible. So then, first up, the general introduction. Now, CReDo lives within this kind of general problem area of how does climate impact our national infrastructure. As you can see on the right here, a few news stories from just over the past couple of years where extreme weather has had severely adverse impacts on the operation of our national infrastructure. So you can see we've got storms introducing power cuts, and then we've got power cuts introducing problems into the supply of our phone networks. And you can see that the national infrastructure can be vulnerable to these kind of extreme weather conditions. We can have unexpected consequences on the operation of this infrastructure. And ideally, we want to see this happening before it happens, rather than lose all this national infrastructure in operation and then have to scramble to get it back online again. And this is something that's been recognised, say, in the Climate Change Committee report here, that I've got a quote from, where they say, whilst understanding of sectoral risk has improved over the last few years, the impacts of climate change could be amplified by the interdependencies between infrastructure sectors, and these interactions are not well understood. So we're talking about how all the different infrastructure networks can have negative impacts, not just within their own systems, but across into other networks. So you've got a small example there where a power cut has knocked out the telephone lines, but this could operate on a whole load of different interconnected systems in our infrastructure, and we want to be able to understand what these impacts are so we can predict them in the future and make ourselves more resilient. So this is a slide that I think Mark used before as well, just kind of demonstrating all the different kind of networks that make up our society today. So say on the base level, we've got the natural infrastructure of the planet, the flood, the rivers, the trees, the soil, all these kind of things. And then on top of that, we've got all the kind of infrastructure which is built by humans and that we know and use day to day, such as the energy networks, transport networks, phone networks, all the things that keep the things ticking day to day. And really, understanding what will happen in these extreme weather scenarios requires understanding of all of these different networks which combine into this single body that forms our infrastructure. So we have a very complicated system composed of lots of different interacting parts that we need to understand the behaviour of. And this poses itself quite well as a digital twin kind of problem. So this is what CReDo was. It is a climate resilience demonstrator, and it's a climate change adaptation digital twin. And we wanted to look at how we can combine these data from all these different infrastructure networks into a single representation, capture the behaviour of all the different infrastructure networks, and then look at modelling the impact across these different networks. So you can see here that we're looking at taking data from Anglian Water, who have the water and sewage networks and all the connections between them. We've got BT, which has all the communication networks, and we've got the UK power networks, which tell us where all the power stations are, the power that runs between them, and what they're supplying energy to. But then on top of that, we want to start adding in flood data. So we want to look at what the different climate scenarios are. We want to model what the weather conditions will be like and what that will mean for flooding in the future. And then into that model, we want to look at what the impact of these floods will be on the infrastructure, so on an individual asset, what will fail, propagate this through the whole system, so we can look at this system's behaviour, and then crucially, look at the outputs of that to be able to decide what can we do to prepare, what responses would actually help, and where do we need to be prioritising our efforts and expenditure to best get our returns to improve resilience in the future. And in order to do that, we had to bring a lot of people together. So CReDo was a big project. They all fit under the National Digital Twin programme, which Mark introduced before. we've got a really big priority on not just building a digital twin for a purpose, but prioritising on it being reusable and interconnected with all of the digital twins. So say we have a digital twin for each of the networks, we want to build it in a way that it can be connected to all these other different approaches in the future. We had several funding bodies that were involved in it, and then the Connected Places Catapult, who now own CReDo. And then crucially, there's all these different partners with all the different expertise. So you can see we've got the asset owners with their own infrastructure data. We've got lots of academic partners with experience in modelling of the different behaviours. So we've got Hartree, we've got CMCL, who did a lot of the work building the software infrastructure. And then we've got DAFNI, which hosted it all. So what is CReDo? We've got a general schematic of what the digital twin is here. So firstly, in the background, all this is running on DAFNI. What we needed to build was a digital twin that was adaptable to lots of different data sources, could run lots of different models for different scenarios, and could be adaptable for different workflows for different problems. So this really kind of fitted into the general DAFNI workflow. So you can see all these things are hosted on DAFNI itself. Then we needed to get the data onto the DAFNI system. So you can see we're taking the asset data from Anglian Water, BT and UK Power Networks, moving it onto DAFNI. We're able to get a custom data set up to ensure the security for this real asset data on DAFNI. And then we're also able to get climate data and run this through HiPIM simulations to get our predicted flood depths into our data store on DAFNI, so that we can access this and get our information on flood depths at different locations. Now, the general approach to how we wanted to model this was that we have this data store of kind of static data sets, and then through iterating through the duration of a flood, we want to model how this flood evolves. So we use this knowledge graph approach, which was led by CMCL, which is your kind of central data repository and represents all the entities in your data set. But there's mainly two big parts into how you actually model the ongoing behaviour of the flood. So we have an individual asset failure model, which looks at individual assets, say a power station or a pumping station, and looks at extracting the information that really models what makes that asset fail. So the approach that we used for that was using Bayesian networks. So through conversations with different asset owners and using academic expertise in this area, we were able to take the information that the practitioners had in their head, because we don't have data on all these floods. It's quite a small number of events. You really need to take the information that people know and able to kind of elicit the structure of interdependencies that cause failure in these devices. And crucially, that's also a probabilistic approach. So instead of just being a one-off deterministic output, you can really start looking at the kind of distribution of outcomes and start trying to quantify your risk. But that only describes a single asset. We want to start looking at the system-wide impact models as well. And this is where work from the University of Edinburgh came in, where we start looking at saying, so we know a single asset's failed, how does that propagate through the network? And really start propagating the impacts from, say, a power station going down, what other networks may fail, even though at their location the flood might not have impacted the asset himself, and getting that interconnected behaviour between all the different networks, and really start looking at these different infrastructure networks, how they combine into a single whole. And then finally, when we update this back into the knowledge graph, we can then run our visualization tool, which is going to be demonstrated by Jethro in the next section, and I'll hand over to him now to show you what this looks like to the end user.
Thanks, Ben. Hi, folks. So I'm Jethro Akroyd from CMCL Innovations. I led the team that implemented many of the knowledge graph aspects of the CReDo digital twin, and I'd like to show you the visualization that we've created and use it to demonstrate some of what the digital twin can do. So the visualization is map-based. It's fully integrated into the DAFNI platform, but there are also previews available on the internet, so you can go and have a play in your own time by following those links if you're interested. Zooming in on the area of interest that we looked at, the visualization and the underlying digital twin is able to represent assets from each of the telecoms, energy, and water networks. And it's able to represent the connectivity between each asset. And at this point, I should emphasize that during the development work of the digital twin, we worked with real data from the asset owners. But I do want you to understand that what you're seeing on screen is synthetic data. So it shares the characteristics of the real data, the same types of assets, the same types of connectivity, but it is fictional. I'd also like to emphasize that what you're seeing on screen in many ways resembles the data structure of the knowledge graph that underlies the CReDo digital twin. The knowledge graph is built using a hierarchy of ontologies, and at the top of the hierarchy is an ontology that we use to define generic concepts. We then, for each asset network, defined specializations for that particular network. And this design confers a number of advantages, mainly that the ability, the abstraction provided by the generic ontology allows us to create interoperability between the data and a design that is extensible and would eventually accommodate other asset owners or other asset types. So I've a lot to say about knowledge graphs, but ask me questions later if you're interested. The main thing that we do with the asset data is integrate it with information for different flood scenarios. And in this case, I'm going to look at a simulation of a 1 in 100 year storm subject to worst case climate projections for the year 2070. I can cherry pick the time point that's of most interesting to look at. And you can now see, I hope you can see at least, the flood depth represented by the depth of color on screen, with most of the floodwater concentrated on the left-hand side of the screen. You'll also see that many of the assets are now picked out with red rings. And the meaning of a red ring is that an asset has experienced some form of failure. And we can click on an asset to find out what's happening. I'm going to click on the asset in the middle. It's a secondary substation. This brings up metadata about the asset, including its name, its location, and a measure of its connectivity in the combined asset network. It also brings up information about the state of the asset. And you can see, if you're lucky enough to be able to read it, you'll see that this asset has lost power, but it isn't actually flooded. The water depth at this location is being reported as 0 meters. And we can interrogate the digital twin a bit further to find out what's happening. We can look at the direct connections to this asset. And if we do that, we can see that it has the possibility of being fed by one of 2 possible primary substations, both on the left-hand side of the screen. So there are 2 possible supply routes. So there's some apparent resilience in the design of this network, yet we know these things have failed. And we can click on the primary substations to find out what's happening. And we can look at the time history of the flood. If we do this, we can see that the primary substation at the bottom of the screen is actually in very deep flood water. The water there is over 1 meter deep. The same is true of the other primary substation, and the fact that both of these are flooded is what then causes the original secondary power station that we looked at to fail, despite the apparent resilience in the network. So, going back to the secondary substation, we've understood why this has lost power, and as a consequence of this, we can see that the things connected to it, so there's a telephone exchange and 2 sewage pumping stations, also fail. So this is an example of how these failures may cascade between networks outside of the area that was originally flooded. And I should emphasize that although this example is using synthetic data, this example is modeled on something that we saw when we were working with the real asset data. The other point that I just want to emphasize is that the CReDo digital twin is able to link to other digital twins to enhance the capability. And I'm going to show 2 examples, both of which are based on work that was performed in collaboration with Marcus Kraft at the University of Cambridge. And in the first example, we show that we are able to link to a digital twin that was created that represented live streams of data from sensors showing river levels reported by the Environment Agency. And on the panel on the right, I realise it's a bit difficult to read, but you can see river level information from one of these sensors. And this data is from the last 6 hours of Storm Franklin. And just before you panic seeing the decrease in river level, I should also point out that this is a tidal river and it's an outgoing tide. In the second example, we demonstrated that we were able to pull in open data describing buildings from Ordnance Survey. And at the top of the screen, you can see a large hospital. And the idea behind doing this is that if we can extend the description of the asset networks to describe which buildings are supplied with which services from which assets, we can then build this into our description of the criticality and therefore help the asset owners better understand the criticality of their assets within the wider built environment. So I hope this has given you a flavour of what we've been able to achieve within the last few months of the CReDo project. At this point, I'd like to hand over to Jens. Thank you, Jens.
Thank you, Jethro. So Jethro just showed what we were able to achieve in the project. So the next question is, how were we able to achieve this? So this is the slide that Ben showed earlier, and now we're going to zoom in on that bit with the asset data store, where we actually put the data from the asset owners. As Brian mentioned this morning, the role of DAFNI was really to be the trusted third party that all the asset owners could give their data to, and we could then process that securely. So people like Jethro could log in and they could do their processing and build their models and stuff. And all of that is done in a trusted way so that the asset owners know where their data is at all times. So we built this essentially by building an extra bit of DAFNI that we put in parallel to the normal DAFNI workflow, the normal DAFNI infrastructure. So in this picture, the blue stuff is sort of, if you're already DAFNI users, and 3/4 of you are DAFNI users, we know from the poll this morning. So the blue bits are things you will recognize. The front end to DAFNI where you will log in, the data repository, and the actual bits where things run, models run, workflows run. In parallel, these sort of orangey bits, brownie bits here, are extra bits we built just to support CReDo. So for all of those bits, there was a little flag in it saying CReDo use only. So it consists of a virtual private network that was set up just to protect the asset data. It consists of a Windows desktop that we borrowed from another department for a very small subset of users that actually needed to use Windows to analyze the data. And then the secure host where Jethro and his colleagues could do all their work. So if you use DAFNI, you may have built your own models. We heard earlier about how it's a little bit of a fiddly thing to build a model and have it uploaded. But once it's uploaded, then it's very easy to run it because you can build workflows on it, you can load parameters into it, and actually the user interface then is quite friendly. But Brian mentioned this morning that there's another participant in there, because we also want the asset owners to be able to explore their own assets on the system. So really, we want three kinds of users in this project. We want the developers who develop the models. We want the users like Jethro and his colleagues who explore the models and try to infer interesting things from it. And then we also want the asset owners to be able to explore at least their own data. And we were sort of missing the last bit. And essentially, if you remember from the very excellent talk about the digital twins, they were sort of like the digital and the physical world were interconnected, like a yin-yang symbol. And we're sort of missing the yang bit on this one, because we had the secure host where we could put the data, but data was not allowed to leave the secure host by the terms of the data sharing agreements that we were working with. So we had to set up all the normal DAFNI stuff, but the normal DAFNI stuff cannot see the asset owner data because it's sensitive. We had to really parcel that off into a very specific bit where it was not allowed to leave the host, So we haven't really got that feedback loop all the way around from the digital world back into the physical world in this case, because of the sensitivity of the data. So a normal user where we can sit an asset owner down and say, this is a portal, here you log into DAFNI and here you do some stuff. In this case, they can only use the synthetic data. They cannot even see their own data without logging in through the technical path. And the technical path still is too technical for users to actually log in. They need to have some sort of, to be familiar with VPNs and SSH and stuff, and having multi-factor authentication and all the interesting bits that we had to set up to protect the data. So it's kind of a flaw in CReDo 1, a lesson learned. It took us a while to get the data agreement negotiated, but then it was so strict that we can't show the asset owners their own data. Well, we could. We could have to sit them down in front of a browser window or something. But at least it's a step forward. We now have this. We were able to do this by and actually derive interesting results from it, even if most of the results that we can actually show you are based on the synthetic data. So one of the options we investigated was, yes, so we have all this infrastructure where users can log into DAFNI and do some work. We also have the extra bits that we have set up specifically for CReDo for the asset owner data, and then to have a third part into that for the asset owners to explore the data sets. So there are several options that we have investigated here, and we know there's a lot of interest in it as well. From we had a meeting recently with the regulators, Ofcom, Ofgem, Ofwat, DEFRA, the Environment Agency, the Cabinet Office. They're interested in, they tell us they're interested in making data interoperable, making data useful, to learn about the infrastructure. So with the follow-on project with CPC, there's an opportunity for us now to investigate the methods that we can, where we can try to make the data useful also for people who are not technical. And there are several options there. BT suggested a model where asset owners actually hold on to their data, to their own data at all times, and they just communicate impact between each other. There are encryption techniques we can investigate. There's the concept of confidential computing. So there are actually lots of things we can do that we never had time to do in CReDo 1. So with this work, we can actually extend the capabilities of CReDo in CReDo 2, because we can put more security controls into the data and then get, hopefully, to a data sharing agreement that would enable us to do even more. And with that, thank you very much.
Okay, thanks very much then. Thank you.